Hello everyone. In this video, we are going to talk about some statistical basis of data simulation. In this lecture, I'm going to first give a brief introduction to Bayesian statistics, which is the theory of a theory foundation of data simulation we use in the Xu et al. Paper, and the following works in the next few units. By learning the Bayes theorem and Bayesian inference, you will understand why we can get the wisdom from data. After looking at the theory, we will then learn how to apply the theory into an algorithm in optimization problems. That is the macro-chain Monte Carlo algorithm. At the end of this video, we will discuss a little about how to get stable optimization results from MCMC algorithm, that is so-called simulation convergence problem. This lecture is only an introduction to all those topics and will not be very complicated and mathematical. If you want to know more about those topics, you are encouraged to have a look at the references I attached at the end of this lecture. First, let's have a look at Bayes' theorem. In plain words, Bayes' theorem is a method for calculating the validity of a belief. For example, your hypothesis, claims, or propositions. All the calculations in Bayes' theorem is based on the best available evidence. For example, your data, observations, or any information you can get. So we can now have an important first impression on the Bayes theorem. That is, if you want to investigate in a question, you must first to have some initial belief on the validity of the question before you know any related information. Then when you get new data or information from the real world, you will naturally update your thinking over the question, and therefore you are updating your belief over the question. That is the basic character of Bayes' theorem. If we use mathematical language to describe Bayes' theorem, we will get this equation. When talking about the probability of event A will happen given event B has already happened, we can calculate as the probability of B given A times the probability of A over the independent probability of event B. And in this expression, we can actually also see what we discussed in the last slide. The independent probability of A actually is our initial belief. Mathematically, we can call it prior knowledge, and the probability of the probability of B given A actually is the new evidence to update our initial belief. Mathematically, we can call it as a likelihood. Let's have a look at an example what happened to everyone to further illustrate Bayes' theorem. Probably a few months ago, you knew that we are going to have a training course. You were extremely interested in it and prepared to apply for it. Before that, you never have experience in matrix representation of carbon cycle or data simulation. But at the same time, you did have experience in modeling. So here is the question. You may be wondering what's the probability of your success in the training course given you have some modeling experience. Intuitively, different individuals may have different guesses. For example, 50% or even 90% chance of success. Because you have no valid success information of the training course, actually all the guesses are purely guesses out of your intuition or just out of no reason. To better evaluate if you are suitable to this training course, let's suppose you decide to ask Dr. Jiang for relevant information. Now, from Dr. Jiang, you know that actually 80% trainees were successful in the past training courses. And if we conceptualize the possibility of one trainee being successful in the training course as event A, actually we now know the independent probability of event A equals 0.8. At the same time, Dr. Jiang may tell you that for the background of those trainees, only half of them had experience in modeling before the training course. And if we conceptualize the possibility of one trainee having modeling experience before the training course as event B, actually we now know that probability of B equals 0.5. Apart from the above information, Dr. Jiang may also tell you more details that for those who were successful in the training course, actually 56.25% of them had modeling experience before they got trained in our training course. This actually gives the possibility of one's modeling experience, given the trainee had already been successful in the training course. Conceptually, we can express as the probability of B given A equals 0.5625. Let's get back to the equation. If you substitute all the information provided by Dr. Yang, we can actually get the probability we are interested in. We now know that given you have had modeling experience, the probability of your successful can be as high as 90%. That means you are very likely to be successful in our training course. For those who did not have experience in modeling, you may now ask, what's the chances of your success? Will it be very small? Actually, we can also calculate this from the given information. The event B in the equation are now becoming the event of not B. We can get the probability of event not B by calculating 1 minus the probability of B. And similarly, the probability of not B given A equals 1 minus the probability of B given A. After some substitution, we can get the chances of one's success given no previous experience in modeling. It's 70%, still quite high, so don't be nervous. If you pay sufficient attention to our training course, you are very likely to be successful in the training course, no matter if you have had some modeling experience or not previously. In reality, when we are talking about the probability, actually it is rare we are 100% the probability is just a number, for example, like 0.5. For most of the time, we need to discuss the probability distribution. For one hypothesis, we have old knowledge corresponding with the prior probability distribution, and for each data we have observed, we can calculate the likelihood of how likely it will happen, and eventually we can get the new knowledge by combining the likelihood and the prior distribution. That is, eventually we will get the posterior distribution of the hypothesis. We use the so-called posterior probability density function to describe the newly got posterior distribution. More generally, no matter we are talking about events or continuous distributions, Bayes' theorem actually indicates a way for us to update our belief in light of evidence. That is, we can learn from the data to validify or falsify our old knowledge. The posterior probability density function actually describes what we have learned from the data and help us to do decisions and inferences. So after the introduction of Bayes' theorem, let's discuss more specific question in modeling. Suppose we have some reasonable value space of parameters in models. We also have observational data in field experiments. We now want to use the new data to constrain the parameter values so that we can optimize model performance. Then the question is, how can we use the data to achieve such target? If you look at different literature, you may find several answers to this question actually. But under the basis of Bayesian statistics we have introduced, I will recommend the macro-chain Monte Carlo method to do so. So what's a macro-chain Monte Carlo method? Basically, the macro-chain can create a sequence of possible events for you to select which one is mostly close to your data. And the macro-chain Monte Carlo method is an algorithm that helps you to finally determine the stable posterior distribution of the investigated parameters. Let's have a look at another example to further illustrate this. Let's suppose you are an organizer of this training course. Then how would you admit the applicants? Generally, if we are organizing a training course, we may first set up the scopes of the course so that we can define the target group who may be interested in this course. When we do this in our mind, actually we are plotting the perfect figure that for sure will benefit from this course. For example, ideally, we may expect people who are in the carbon cycle community, doing some modeling work, and have already had some research experience. After you define the scope of the training course, you may send out the flyers to attract people. You will receive applications from time to time. After we receive the application material, we may need to evaluate how suitable the applicant to our training course. The perfect figure in our mind now will function as a reference in such kind of evaluation. Roughly, there are three possibilities in the evaluation. One is the background of the applicant is very close to our perfect figure, and will most likely get benefit from this training course. And in this case, we will admit the applicant without hesitation. Another possibility is the background of the applicant is not very close to our perfect figure, but still can get benefit from our training course. In this case, we may consider an algorithm to finally accept or reject the applicant. And of course, we may also receive applications where the background of the applicant is not even close to the scope of this training. And in this case, we can just directly reject the applicant. After we made decision on one application, we will make decisions on the following applications via the same algorithm. We can now split the whole process into three parts. In the first part, actually we initiate the application, and in the second part, we receive the application materials, and in the third part, we make decisions on whether or not accept the application. Actually, we can correspond these three parts with three steps in MC algorithm. The first step is the the so-called initiation, and the second step is the proposal, and the third step is the acceptance. In the initiation step of macrochain Monte Carlo method, basically we are setting the prior range of the parameter values. At the same time, we may have already had observations that contain information to constrain the parameter values. In the second step, we need to propose candidates of parameter value, so that we can select the candidates by a certain algorithm. In MCMC, actually there are two runs to propose the candidates. One is the test run, and another is the formal run. We will discuss later why there are two types of proposal distributions. After the proposal of parameter values, actually we can now evaluate how suitable the proposed parameter value is to the observations. Here we can use a cost function to calculate how the proposed parameter value can explain observations. Basically, if we apply the proposed parameter value into the model, we can get the model simulation results. And if we use the distance of the simulated ones from the observations as the core part of the cost function, we can get this expression. In this case, for each newly proposed parameter value, we can compare its cost function results with the previously accepted ones. If the new cost is smaller than the previous one, we may directly accept the newly proposed parameter value. But if the new cost is larger than the previous one, which means under the new parameter value, the model performance is worse than when the model is using the previously accepted parameter value. In this case, we need to design a criteria to decide whether or not to accept the newly proposed parameter values. Basically, in the MCMC algorithm, in this case, we first generate a random number by the uniform distribution between 0 and 1. After that, we compare the cost function results with the random value. If the random value is smaller than the cost, then we will accept the corresponding parameter value. But if the random value is larger than the cost, we may just reject the proposed parameter value. After all this, we can repeat the process from the proposal step until we get sufficient accepted parameter values. If we assemble all the accepted values, we can get the desired posterior distribution of the parameter. So throughout the steps in MCMC, actually you may have several questions regarding the details. You may wondering in step 2 why we need a test run and a formal run in proposal. Basically, in the MCMC, if we have no knowledge about the parameters, we may just assume that the parameter value ranges in a wide interval and follows the uniform distribution. And therefore, you can use this prior assumption throughout the MCMC. However, it is not very efficient and could be difficult to get the results being converged. So we can first use the uniform proposal distribution in the test run, and after a few iterations, we use the posterior information in the test run as the prior information in the formal run. And in the formal run, we will also change the proposal distribution to the multivariate normal distribution. And such kind of assumptions, the process can be more efficient, and the final results can be more robust. At the same time, you may also ask why in the step 3 we need to assign a possibility of acceptance even when the new cost is larger than the old one. This is because in some cases, the so-called bad results can be helpful in finding the global minimum of the cost. We may first get to the point that has worse results than the previous one, and then we can eventually find the global optimum. If we do not give a chance of acceptance to those so-called bad results, we may easily get trapped in a local optimum, which apparently is not what we desire. Finally, let's discuss the so-called convergence problem in MCMC. Actually, in the first step of MCMC, if you still remember, the start point is a random one. But eventually, after we apply observations to constrain parameter values by MCMC algorithm, no matter where we start, the final results would be pretty much the same. That caused the convergence of the MCMC results. But we may also notice that from the start to a certain time period, the trajectories by different starting points still differ from each other. Only after some certain iterations, for example, like 10,000 iterations, the trajectories can be converged. We call the early stage of the trajectory as the burn-in period. In the final analysis, we may just exclude the burn-in results. For example, like in real practice, we may just eliminate the first half of accepted results as the burn-in as the burn-in period, and just analyze the rest of the rest half of the accepted results. To access the convergence, we can just look at the trajectories by different starting points to see if they eventually overlap with each other. But statistically, we can use statistics to evaluate the convergence. Actually, the GR statistics is a good option. When macro chain converge, the GR statistics will approach the number of 1. The closer, the better. So here comes the end of this lecture. As I mentioned, we only discussed some basic concepts of Bayesian statistics and MCMC algorithm. If you are interested in those series or you want to go deeper about those series, you can have a look at the references listed on the screen. And if you have any questions, please feel free to ask me in the Slack platform or directly contact me by email.